So, here is something happening right now, quietly, in every direction, while you settle in tonight. Every distant galaxy you could point to is moving away from us, not traveling through space towards some far-off destination, but being carried away by the slow growth of space itself. The further away a galaxy is, the faster it recedes. That much has been known for about 100 years. But here is the part that this whole night is about. That drifting apart is not slowing down. It is speeding up. As far as anyone has ever been able to tell, it will never stop. That is a strange thing to say out loud. For almost all of the time, people have thought carefully about the sky. They assumed the opposite. They assumed that whatever the universe was doing, gravity would eventually rein it in, the way a ball thrown upward always slows, and stalls, and falls back to your hand. It seemed obvious. Everything in the cosmos pulls on everything else. Surely all that patient pulling would, in the end, gather the drifting galaxies back, or at the very least bring the expansion gently to rest. That was the reasonable picture. It was a comforting one, because it closed the loop. It gave the story an ending you could hold in your hand. But that is not what we found. And tonight, we are going to sit with what we found instead, slowly, and follow it all the way out to the end. Not the discovery that space is expanding, which is a story for another night. Tonight is about where all of it is going, why the drifting apart never stops, what the universe slowly becomes because of it, and how the whole vast thing finally ends in a dark so complete and so unimaginably far away that the numbers stop meaning anything long before we ever arrive there. You do not have to follow every step. You really don't. There will be large ideas tonight and enormous stretches of time, a handful of names and places to hang the story on. But none of it is a test. If you drift off in the middle of a sentence, that is precisely what this is for. The universe has been doing all of this for billions of years without anyone watching. It will go on doing it long after tonight, whether or not you stay awake to hear how the story ends. So let that take some weight off. Nothing here needs anything from you. Let me give you the shape of it first, softly. So you know the country we are going to walk through. Then you can let the details wash over you as they come. We will start close to home, with the simple fact that space is growing and what that really means, because it is stranger and gentler than it sounds. Then we will go back to a time when everyone was sure the growth was slowing, and watch that certainty quietly fall apart on one night in the late 1990s, when two teams of astronomers went looking for the cosmic breaks and found an accelerator instead. We will meet the thing that pushes, the dark energy that makes up most of the universe, and that nobody can explain. We will follow it out into the deep future, where galaxies slip over a horizon and vanish, one by one, and the sky slowly empties. Then we will keep going, past the death of the last star, past the slow crumbling of matter itself, down into a cold and patient dark, to see how it all comes to rest. Then, at the very end, we will come home, back down through all of it, to this room, to the bed, to the small, warm, gathered together thing that you are. Because here is something worth knowing before we even begin. All of that drifting apart, all that vast and endless spreading out, cannot touch you tonight. The forces that hold you together, that hold this room together, that hold the earth and the sun and our whole galaxy together, are winning easily, here in this quiet corner. The expansion happens out in the great empty spaces between the galaxies, far away, where there is nothing to hold. It does not reach into a warm room on a small world, so you are safe from the whole thing, completely, and you always have been. So let's begin gently, with the fact itself. When we say the universe is expanding, it is very easy to picture the wrong thing. It is natural to imagine all the galaxies as pieces of debris flung outward from some great explosion, flying apart through space the way sparks fly from a firework. That picture feels right, and it is almost entirely wrong. The galaxies are not, for the most part, racing through space. They are sitting more or less still, each in its own patch, while the space between them quietly swells. It is the room that is growing, not the furniture sliding across the floor. That difference, small as it sounds, turns out to be the key to the whole strange story. Think of it this way, since we have all the time in the world. Imagine a loaf of raisin bread sitting in a warm oven, slowly rising. The raisins do not move through the dough. They just sit where they are, held in place. But as the dough rises, the space between every raisin grows, in every direction at once. Pick any raisin to be your home, and watch the others. The nearby ones drift away slowly. The far-off ones drift away faster, because there is more rising dough between you and them to do the pushing. Every raisin sees the same thing. Every raisin thinks it is the still one at the center, watching all the others flee. None of them is right, because there is no center. There is just dough, rising, everywhere, all at once. That is very nearly what the universe is doing, except that the dough is space itself. There is no oven around it, and no edge, and no outside for it to rise into. The space simply grows, from within, everywhere. It carries the galaxies along for the ride, like raisins that never chose to travel. When you look out and see a distant galaxy fleeing from us, you are not special, and neither is it. An astronomer in that galaxy, looking back at ours, sees exactly the same thing. We are both being carried apart by the same slow rising. Both of us, quite reasonably, feel like the one standing still. Now, you might reasonably wonder how anyone could possibly know this. The galaxies are so far away. They move so slowly by the standards of a human life that you could watch one your whole life and never see it budge. The answer is hidden in their light. It is one of the quietly beautiful tricks in all of science. When light travels across a stretch of space that is growing, the light gets stretched too. Its waves are pulled longer, and longer waves of light are redder light. So the light from a galaxy that is being carried away from us arrives a little redder than it left. The astronomers call this redshift, and the further away a galaxy is, the more its light is reddened, because it has crossed more growing space to reach us. You look at a smudge of distant light, you measure how far its color has been pulled toward the red. The space itself tells you how fast that galaxy is receding. The universe writes its own speed into the light, if you know how to read it. This was worked out in the 1920s, mostly through the effort of an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, with the largest telescope in the world at the time. He found that nearly every galaxy was redshifted, fleeing from us, that the more distant ones fled faster, in a clean and simple proportion. A Belgian priest and physicist named Georges Lemaitre had reasoned his way to much the same conclusion a couple of years earlier, from the equations alone, and had even guessed that it all pointed back to a single beginning. For a long time, Lemaitre's name was left off the result. The way the first person to see something is so often quietly forgotten, while the story keeps the second. But the two of them together, the observer and the priest, gave us the picture we still hold. A universe that is not sitting still. A universe that has been growing for as long as it has existed. Here the mind snags on a very natural question, so let's take it gently and set it down. If the universe is expanding, what is it expanding into? What lies outside it, waiting to be filled? It feels like there has to be an answer, some vast empty room that the swelling cosmos is spreading through. But there is not. And the honest answer is stranger and calmer than that. There is no outside. Space is not expanding into anything, because space is not a thing sitting inside a bigger emptiness. Space is the emptiness. When we say it grows, we mean that the distances measured inside it grow. There is simply more room between things than there used to be. There will be more still tomorrow, and the question of what is beyond the edge dissolves. Because there is no edge to be beyond. It is a hard idea to hold, and you do not have to hold it. Let it be strange. Strangeness is restful when nothing depends on your solving it. So that is where the 20th century found itself. The universe was growing. The moment you know that, a single enormous question opens up in front of you. It is the question this whole night circles around. If everything is drifting apart, where does it end? Does the drifting go on forever? Or does it, someday, slow and stop and reverse? For most of the last century, the smart money was firmly on stopping. The reasoning was so clean that it was hard to argue with. Gravity, remember, only ever pulls. Every galaxy tugs on every other galaxy across the void, all of that mass reaching out to all of that other mass. Always inward, always trying to gather things back together. So the expansion, whatever had set it going, was fighting against the combined gravity of everything in the universe. That meant it had to be slowing down. It simply had to. The only question, the whole game, was how much. How strong was the pull? Whether it was strong enough to win. Astronomers turned that question into a tidy set of 3 possible futures. For decades, those 3 futures were the entire debate about how the universe would end. It all came down to a single number, the average density of matter spread through space, weighed against how fast the universe was expanding. Pack enough matter into the cosmos, and its gravity would be strong enough to halt the expansion and pull everything back. Too little, and the expansion would coast onward, slowing forever, but never quite stopping. And balanced exactly on the knife edge between them was a third, perfectly poised case. There was even a name for that critical amount of matter, the exact density that sat on the boundary. Everything hung on which side of that line the real universe fell. Picture the 3 endings, because they are worth seeing clearly before we watch reality refuse all of them. In the first, there is plenty of matter, and gravity is strong. The expansion slows and stalls, and then quietly reverses. The galaxies, which had been drifting apart, begin to drift back together. Over unthinkable ages, the whole universe falls inward. The sky grows brighter and hotter. Everything collapses back into a single dense point, a mirror image of the beginning. They called this the Big Crunch, a universe that breathes out and then breathes in. Some people found it bleak. Others found it strangely comforting, because it meant the cosmos might do it all again, expand once more, live another life in an endless cycle of breaths. In the second ending, there is too little matter, and gravity is too weak to win. The expansion never stops. It slows and slows, drifting apart more and more gently, forever, but always coasting outward, a ball thrown so hard it escapes the earth entirely and never falls back. This was the open universe. It grows cold and thin and lonely over endless time, but it never turns around. In the third case, the balanced one, the universe expands at exactly the escape speed, slowing forever, creeping toward a stop it takes an infinity to reach but never quite achieves. A universe walking to a halt it never gets to. 3 futures: a turning around, a coasting on, or a slowing to an endless crawl. And notice what every single one of them has in common, because it matters for the surprise that is coming. In all 3, the expansion is slowing down. In all 3, gravity is the master, and the only argument is over how completely it wins. Nobody, in all those decades of careful thought, seriously imagined a fourth possibility. Nobody expected the expansion to be getting faster. Why would it? What could possibly be pushing? There was nothing in the picture to push. And so the whole task, the great project of 20th century cosmology, became to measure the amount of matter, the rate of slowing, carefully enough to find out which of the 3 quiet endings we were headed for. It felt like tidying up. It felt like the last chapter. It turned out to be nothing of the kind. To measure the slowing, you need to look very far away. And looking far away, in astronomy, means looking far back in time. Light is slow, by cosmic standards. The light from a galaxy, 1 billion light years away, has been traveling for 1 billion years. So you are not seeing that galaxy as it is now. You are seeing it as it was 1 billion years ago, when the light set out. Look far enough, and you are looking at the young universe directly, caught in the act of whatever it was doing back then. So if the expansion had been faster in the past and was slowing down, the deep past should carry the fingerprints of that faster growth. All you had to do was find something far away, whose true brightness you already knew, measure how faint it looked, and compare. The gap between how bright it should be and how bright it seemed would tell you how much the space in between had stretched, and how the stretching had changed over the eons. The trouble, as always, was finding something whose true brightness you could trust across billions of light years. Ordinary stars are far too faint to see at those distances. You need something that flares up bright enough to be seen halfway across the universe. That always flares to very nearly the same brightness, so that you can treat it as a fixed candle held up in the dark. So is there anything in the universe bright enough and steady enough to trust across such distances? There is, as it turns out. It is one of the most useful objects in all of cosmology. It is a particular kind of exploding star, called a Type 1, a supernova. Here is how one is made, because it is a lovely and precise piece of clockwork. Take a white dwarf, the small, dense ember left behind when a star like the sun dies and quietly sheds its outer layers. A white dwarf is about the size of the Earth, but as heavy as a star. On its own, it will simply sit there and cool for ages. But if it has a companion star nearby, it can slowly pull matter off that neighbor, stealing gas and growing heavier and heavier. A white dwarf has a strict limit to how much it can weigh. When it creeps up to about 1 2/5 times the mass of the sun, a threshold worked out by a young physicist named Subramanian Chandrasekhar, it can no longer hold itself up. It detonates, all at once, in a runaway burning that tears the whole star apart and for a few weeks outshines an entire galaxy. And because that detonation always happens at the same tipping point, at the same critical weight, every Type 1a supernova explodes with very nearly the same true brightness. That is the gift. They are standard candles, scattered through the depths of space and time, each one flaring to a known and trustworthy brilliance before fading away. Find one in a distant galaxy. Measure how faint it looks from here. You can read off, with real precision, how far away that galaxy is and how much the universe has stretched since the light began its journey. It was exactly the tool the century had been waiting for. In the 1990s, two rival teams set out, independently, to use it to catch the universe in the act of slowing down. One team was based at the Lawrence Berkeley Laboratory in California, led by a physicist named Saul Perlmutter. They called themselves the Supernova Cosmology Project. They had been at it since the late 80s, slowly building the painstaking methods needed to find these rare, fleeting explosions on purpose in galaxies billions of light-years away. It is harder than it sounds. A supernova appears without warning, shines for a few weeks, and fades. To catch enough of them, you have to photograph huge fields of thousands of distant galaxies, then come back later and photograph them again, and compare the two, hunting for a new pinprick of light that was not there before. For years, it was slow, thankless work, with the machinery and the funding and the sheer statistics all fighting against them. The second team formed a little later, in the mid-90s, partly in response to the first. It gathered together some of the sharpest observational astronomers in the field. It was led by Brian Schmidt, a young American astronomer who had moved to the Australian National University. It drew on the expertise of a Harvard group around Robert Kirshner and included a gifted young researcher named Adam Rees. They called themselves the High Z Supernova Search Team, the Z standing for redshift, the measure of how far the light had been stretched. The two teams were competitors, sometimes sharply so, racing to reach the same answer first, watching each other's moves, occasionally trading accusations across the small world of supernova astronomy. What makes the story worth telling is that both of these rival groups, working separately, with different people and different methods, and every reason to want to beat the other, ended up staring at the very same impossible result, at very nearly the same time. Both teams expected the same thing. They expected deceleration. Everyone did. The whole point of the exercise was to measure how much the expansion had slowed since the distant past, to weigh the universe and find out which of the three quiet endings we were bound for. A decelerating universe makes a specific prediction. If the expansion had been faster long ago and gravity had been reining it in ever since, then a distant supernova should appear a certain way. The space its light crossed would have stretched by a definite, calculable amount. The supernova would look a particular brightness for its redshift, slightly brighter, in fact, than it would in a universe that simply coasted. That was the number to beat. Measure the faint far-off candles, plot their brightness against their redshift, and read the deceleration straight off the curve. It was, everyone assumed, a matter of pinning down which slowing universe we lived in. Nobody was looking for a surprise. They were looking for a decimal place. That is the thing about the deepest surprises in science. They almost never arrive as a bolt from the blue, announced by someone hunting for revolution. They arrive quietly, in the middle of careful, ordinary work, when a trusted measurement comes back wrong in a way that will not go away. Someone checks the equipment. Someone checks the math. Someone stays late, running the analysis again, certain there is an error, because the alternative is absurd. The number sits there, patient and impossible, refusing to be talked out of what it is saying. That is what began to happen, on both teams, as the distant supernovae came in, one by one, through the middle of the 1990s. The pattern in the data slowly, stubbornly, refused to look like anything anyone had planned to find. The distant supernovae were coming in too faint. That was the whole of it, at first. Just that small, quiet wrongness. The far-off exploding stars looked dimmer than they should, which meant they were farther away than they should be, which meant the light had crossed more stretched space than anyone had allowed for. There is only one way to fit more stretching into the history of the universe than a slowing expansion permits. The expansion could not have been slowing. It must have been speeding up. Not long ago, but through the whole second half of the universe's life, the drifting apart had been getting faster, gently, steadily, pushed along by something nobody could name. You have to understand how unwelcome that was. It was not a result anyone wanted, and it was certainly not a result anyone was looking for. Adam Rees on the High Z team was running the numbers through the winter of 1997. The answer that kept falling out was an expansion that was accelerating, which in the language of the equations showed up as a strange negative amount of deceleration, a slowing that was less than nothing. He assumed, reasonably, that he had made a mistake. He checked it. He checked it again. He wrote, later, that the value his own analysis was handing him seemed absurd, that he spent weeks trying to find the error that would make it go away. There was no error. The universe simply was not doing what 100 years of good sense said it had to do. Across the state and across the ocean, the other team was arriving at the same place by a different road. Saul Perlmutter's supernova cosmology project, which had been grinding away the longest, was seeing the same faintness in its own distant candles. Two rival groups, who did not much want to agree with each other, who had every professional reason to be suspicious of a claim this large, especially one first announced by the competition, were nonetheless both looking at data that said the same impossible thing. That is the part that makes it believable. When two teams who are racing each other, using different stars and different methods, both stumble into the same answer that neither of them wanted, the answer starts to look less like a mistake and more like the world. The word went out through 1998 and into the following year. In a pair of papers and a scatter of conference talks, cautious and hedged the way careful people are cautious when they know how strange their result is. The expansion of the universe is accelerating. The galaxies are not just drifting apart. They are drifting apart faster with every passing age. The community did what a healthy science does with a claim like that. It did not celebrate. It doubted. People looked for the ordinary explanations first, as they should have. Maybe the distant supernovae were not quite as standard as the nearby ones. Maybe some veil of dust was dimming the far-off light and faking the effect. Maybe the young universe made its exploding stars a little differently. Each of those worries was real, and each was chased down, tested, and one by one set aside, because the acceleration kept surviving every check, and because other, completely separate lines of evidence began, over the next few years, to point at the very same conclusion. That is what finally settled it. Not the supernovae alone, but the way they agreed with everything else. Careful maps of the faint afterglow of the Big Bang, the ancient light called the cosmic microwave background, showed that the universe was very nearly flat, which demanded a certain total amount of stuff filling it. When astronomers added up all the matter they could find, ordinary matter and the mysterious dark matter together, it fell far short of that total. Something else had to be making up the difference, something that was not matter at all, something spread evenly through all of space. When they asked what that missing something would do to the expansion, the answer came back the same. It would push. It would drive the very acceleration the supernovae had already found. 3 separate roads, the exploding stars, the ancient light, the accounting of everything the universe is made of, all arrived at the same quiet door. There is something in empty space that pushes it apart, and it is winning. In 2011, more than a decade after the result, the Nobel Prize in Physics went to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion. By then, the finding had reshaped everything. The tidy, century-long project of measuring the deceleration, of choosing between the crunch and the coast and the endless crawl, was simply over. All three of its careful endings were gone, swept off the table by a single stubborn faintness in the light of dying stars. In their place stood a stranger universe and a stranger future. One enormous question that we still cannot answer. What is doing the pushing? Because that is what an accelerating universe demands. If the expansion is speeding up, then something is driving it, working against the gravity of everything, spending energy to hold the galaxies apart and to push them apart harder over time. Gravity pulls things together. That much we understand. But here was the whole cosmos being pried open, gently and relentlessly, by a force that pushes outward, that lives in the empty spaces, that grows more dominant the emptier those spaces become. It needed a name even before anyone understood it, because you cannot talk about a thing you refuse to name. The name they gave it was deliberately humble, almost a confession of ignorance dressed up as a term. They called it dark energy, not because it is dark in the way of a shadow, but dark in the way of a thing we cannot see, cannot make in a laboratory, and cannot yet explain. A placeholder word for the largest ingredient in the universe. It is the largest, by a long way, which is the detail that never quite loses its strangeness. When you take the whole universe and ask what it is made of, the ordinary matter, the stuff of stars and planets and people and every atom you have ever touched, comes to only about 5 parts in 100, a 20th of everything. The mysterious dark matter, whatever it is, that vast unseen scaffolding whose gravity holds the galaxies together, makes up something like a quarter more. All the rest, a bit more than 2/3 of the entire contents of reality, is this dark energy. The thing we understand least is the thing there is most of. We are a small, bright, rounding error, living inside a universe that is mostly made of a mystery. The mystery is quietly pushing the whole thing apart. So what is it? The honest answer, the one you should hold on to through everything that follows, is that we do not know. But we have a leading suspect. It comes with one of the better stories in the history of physics, a story about a mistake that turned out not to be one. To tell it, we have to go back before Hubble, before anyone knew the universe was expanding at all, to Albert Einstein, sitting with the equations he had just finished writing down. In 1915, Einstein gave the world a new theory of gravity, the general theory of relativity, which describes gravity not as a force reaching across space, but as the bending of space and time by matter. It is one of the deepest things anyone has ever worked out. It has passed every test we have ever put to it. But when Einstein applied his own beautiful equations to the whole universe at once, they told him something he did not want to hear. They said the universe could not sit still. It had to be either expanding or contracting, growing or shrinking, but never simply resting. This was 1917. Everyone, Einstein included, knew for a fact that the universe was static, eternal, unchanging. The idea that it might be growing was not yet even a question. So Einstein did what a person does when a trusted tool gives an answer that contradicts an obvious truth. He decided the tool needed adjusting. He added a term to his equations, by hand, a small extra piece with no other justification than that it made the answer come out right. It represented a kind of uniform pressure spread through all of space, a gentle outward push built into the emptiness itself, tuned to exactly balance the inward pull of all the matter, so that the universe could hold still after all. He called it the cosmological constant, and he gave it the Greek letter lambda, and with it, his static universe was saved. It was, by his own later admission, an ugly patch. But it worked, and for a while it let everyone keep the calm, eternal cosmos they were sure they lived in. Then, about a decade later, Hubble and Lemaitre showed that the universe was not static at all. It was expanding, exactly as Einstein's untouched equations had tried to tell him before he tinkered with them. If he had trusted the plain mathematics, he could have predicted the expanding universe years before anyone measured it, one of the greatest predictions never made. Instead, he had papered over it to fit a picture that turned out to be wrong. He dropped the cosmological constant, apparently with some embarrassment. The physicist George Gamow later reported that Einstein had called the whole episode his greatest blunder, though we only have that at second hand. It may have grown in the telling the way good lines do. Either way, lambda was set aside, a fudge factor from a more ignorant time. For 70 years it sat quietly in the history books, a cautionary tale about forcing the math to agree with your prejudices. Then, in 1998, the supernova brought it roaring back. Because when astronomers asked what kind of thing could make the expansion accelerate, the simplest answer, the one that fit the data with the least fuss, was almost exactly the term Einstein had invented and thrown away. A constant energy woven into empty space, pushing outward, everywhere, always. His blunder, it turned out, was real. He had just gotten the size and the sign a little wrong, and had used it to hold the universe still when its true job was to blow the universe apart. The ugliest patch in his beautiful theory was quietly waiting all along to be the description of the thing that governs the fate of everything. So the leading idea for dark energy is that it is this, the energy of empty space itself. That phrase deserves a moment, because it sounds like a contradiction. How can empty space have energy? Is it not, by definition, nothing? But modern physics has learned, in 100 separate ways, that empty space is not truly empty. Down at the smallest scales, the vacuum seethes with restless activity, with fields that can never quite settle to zero, with particles that flicker in and out of existence too quickly to catch. Space that has been swept perfectly clean of every atom and every scrap of light still hums with a faint baseline energy that cannot be removed, because it belongs to the space and not to anything in it. And energy, according to Einstein's own theory, has gravity, usually gravity that pulls. But this particular kind, the energy of the vacuum, has the strange property that its gravity pushes. It has, in the language of the physicists, a negative pressure, and negative pressure, spread through space, drives everything apart. You do not need to follow the machinery of why. It is enough to know that empty space appears to carry a gentle outward pressure built into its very nature. That pressure is what we call dark energy. There is one enormous problem with this lovely idea, and it is worth mentioning, gently, because it is the kind of open wound that makes the whole subject honest. When physicists try to calculate how much energy the vacuum should have, using their best theories of the very small, they get an answer. The answer is wrong, not a little wrong. It is too large than what we actually observe by a factor so vast it is almost comic, a number followed by something like 120 zeros. It is often called the worst prediction in the history of physics, this gap between what the theory says the energy of empty space ought to be, and the tiny, delicate amount that is actually out there gently pushing the galaxies apart. So we are in the strange position of having a suspect that fits the crime almost perfectly, while being completely unable to explain why the suspect is the size that it is. That, too, is a thing you are allowed to simply rest in tonight. The largest ingredient in the universe is a mystery wrapped around a puzzle. No one is going to solve it before morning, least of all you. But here is the property that matters for our story, the one thing about dark energy that we can be fairly confident of. It is the hinge on which the whole future turns. Whatever dark energy is, it appears to be a property of space itself, not of the matter in space, but of the empty room, which means that a given amount of empty space carries a given amount of this pushing energy, and always has, and always will. That innocent little fact, that dark energy belongs to space rather than to stuff, is the reason the drifting apart can never stop. Think about what happens to ordinary matter as the universe grows. Picture a certain amount of it, a scattering of galaxies filling a region of space. Now let the space expand, let it double in size in every direction. The galaxies are still there, the same galaxies, the same total amount of matter, but they are spread through a volume that is now 8 times larger, because doubling the size in all 3 directions multiplies the room by 8, so the matter is thinner. Its density has dropped, and gravity depends on density, on how much mass is packed into how much space. So as the universe expands, the pull of gravity, spread ever thinner, grows weaker and weaker. Matter is always losing ground, always being diluted, always relaxing its grip a little more with every stretch of the growing space. Now do the same thing with dark energy and watch the difference, because everything hangs on it. Dark energy is not a scattering of stuff sitting in space. It is a property of the space itself, a fixed amount of pushing energy in every empty box of a given size. So when the space doubles, you do not spread the same dark energy thinner. You make more space, and every new patch of space comes with its own full measure of dark energy, freshly included, at the same density as before. The pushing does not dilute. Double the universe, and you simply have twice as much of the stuff that pushes, at exactly the same strength per unit of room. Its density holds perfectly steady, forever, no matter how large the universe grows. There is the whole future, hidden in that one contrast. On one side, gravity, tied to matter, growing weaker with every passing age as the matter thins out. On the other, dark energy, tied to space, holding its strength no matter what. It is a tug of war between a force that fades and a force that never tires. And who wins a contest like that? You do not need to be told. It is only a question of when. For the first several billion years after the beginning, matter was densely packed, gravity was strong, and it was actually winning. The expansion, in those early ages, really was slowing down, just as everyone had assumed it always would. But the matter kept thinning, and gravity kept fading, and dark energy kept holding, until a few billion years ago, the two forces passed each other, and dark energy took the lead. That is the moment the universe stopped slowing and started to accelerate. We are living in the long aftermath of that crossover, on the far side of the turning point, in the age when the pushing has already won. And once it has won, it does not just win. It compounds. Follow the logic all the way, gently, because it is the engine of the entire story. Dark energy pushes space to expand. The expansion makes more space. More space means more dark energy, since the density stays fixed. More dark energy means a stronger total push. A stronger push makes the space expand even faster. Faster expansion makes even more space, which makes even more dark energy, which pushes even harder. It is a wheel that turns itself, an engine that runs on its own exhaust. There is nothing in the picture to slow it down, because the one thing that could slow it, gravity, is being thinned into irrelevance at the very same time. This is what the physicists mean when they say the expansion is not just continuing, but accelerating, and will go on accelerating without end. The universe is settling into a kind of growth where every stretch of space breeds more stretching, endlessly, in a doubling that keeps on doubling. That is the shape of a universe ruled by a constant dark energy. It has a clean and slightly chilling name in the equations. It approaches what is called a de Sitter universe, after the Dutch astronomer Willem de Sitter, who first found this kind of empty, exponentially growing solution in Einstein's equations long before anyone knew it might describe reality. In such a universe, distances do not just grow. They grow by a fixed fraction in every fixed span of time, which is the signature of runaway. Wait long enough, and any 2 points, however close, are hurled apart faster and faster and faster, forever. The growth has no ceiling, no turning point, no gentle coasting to rest. It is the mathematics of a thing that never, ever stops. So take a moment to feel where this leaves us, resting here at the far side of the crossover. Remember the 3 quiet endings that the whole 20th century had laid out. The big crunch, where gravity wins and everything falls back together. The endless coast, where gravity nearly wins and the expansion drifts to a crawl. The balanced case, walking to a halt it never reaches. Every one of them assumed gravity was the master, and the only question was the margin of victory. Every one of them is gone, not modified, not refined, but simply crossed out, because there was a 4th possibility that no one had thought to draw on the chart. It turned out to be the one we live in. The expansion does not slow. It does not stop. It does not reverse. It speeds up, and it will keep speeding up, as long as dark energy remains the thing it appears to be, until the end of time, which in this kind of universe is not really an end at all, but an unbounded, ever-accelerating, spreading out into the dark. And I want to be careful and honest here, because this is a sleep story, but it is also meant to be true. The truth has an edge of doubt on it that we will come back to properly near the end. Everything I have just said rests on one assumption: that dark energy really is a constant, an unchanging property of space that never varies. That is our best current picture, and most of the evidence supports it. But it is an assumption, not a certainty. There are very recent hints, which we will sit with later, that dark energy might not be perfectly constant after all. If that turned out to be true, the ending could be gentler or stranger than the one the constant implies. For now, though, hold the standard picture, the one the numbers most naturally give. A universe drifting apart, faster and faster, without end. And let's go and see what that actually does to the sky, because the consequences are quieter and more beautiful than the word runaway makes them sound. Here is the first strange consequence, and it is one that trips people up. So let's walk into it slowly. The further away a galaxy is, the faster the space between us and it is growing, and therefore the faster it recedes. Nearby galaxies drift away slowly, distant ones drift away quickly, and very distant ones drift away very quickly indeed. Now follow that all the way out. If recession speed keeps climbing with distance, then there must be some distance, far enough away, where the space is growing so fast that the galaxies out there are receding from us faster than the speed of light. And your first instinct is to say, That cannot be right. Nothing can travel faster than light. That is the one rule everyone knows. So, how can whole galaxies be fleeing faster than light itself? But look carefully at what is happening, because the rule is not actually being broken. Those far-off galaxies are not moving through space faster than light. In their own patch, each of them is sitting more or less still, no atom of them racing anywhere. It is the space between us and them that is expanding. It is expanding at every point along the enormous distance in between, and all that expansion adds up. Enough stretches of growing space, laid end to end. The total recession can outrun light, even though nothing local is moving quickly at all. The cosmic speed limit governs how fast things move through space. It says nothing about how fast space itself may grow. And space, it turns out, is allowed to grow as fast as it likes. So there are galaxies out there right now, real galaxies full of stars, that are receding from us faster than light. That has a consequence you can feel in your chest a little, even lying here in a warm bed. The light leaving those galaxies tonight will never reach us. It is swimming toward us as fast as light can swim. But the space it has to cross is being added ahead of it faster than it can cross the space behind it. It is a swimmer heading for a shore that is being pushed away faster than she can stroke. She will swim forever and never arrive. And so the light from those galaxies, set out with such speed in our direction, will fall behind and stretch and fade and simply never get here. Not tonight, not in a billion years, not ever. The distance at which this happens has a name. It is called the cosmic event horizon, and it is one of the gentler and sadder ideas in cosmology. It is not the edge of the universe, and it is not the edge of what we can see. It is the edge of what can ever reach us. Everything inside it can, in principle, still send its light across to us someday. Everything beyond it is cut off forever, its light forever losing the race. Right now, in the present universe, that horizon sits at a distance of roughly 16 billion light years. It is worth being careful here, because it is easy to muddle this with another number you may have heard, the size of the observable universe, which is much larger, something like 46 billion light years across in radius. Those are different things, and the difference is the whole point. The observable universe is everything whose light has had time to reach us since the beginning, the whole vast archive of the past that is currently arriving. The event horizon is the smaller boundary of everything whose light can still reach us from here on out, into the whole infinite future. We can see far more of the universe than we can ever touch, or ever hear from again. It is worth letting one fact land here, gently, because it makes the whole idea real in a way the word horizon does not. When you look up at the darkest sky, or at the deepest images our telescopes have ever gathered, you are seeing the light of something like 2 trillion galaxies, an almost meaningless abundance of them, filling every black gap with faint smudges of ancient light. The sobering truth is that the great majority of them are already beyond our reach, not gone from view, not yet, but gone in the only sense that finally counts. They have already crossed the cosmic event horizon. The light we see from them tonight is old light, set out long ago, still crossing the space between, still faithfully telling us they are there. But if we could send a signal toward them at the speed of light, this very instant, it would never arrive. Most of the galaxies scattered across the sky, we are seeing only as they once were, in light that is still in transit, from places we could already never travel to, and never call, not in a billion years, not ever. only a small sliver of everything visible remains close enough that we could still, in principle, reach it or hear back from it. The doors did not begin closing in some far-off future. For most of the universe, they closed a long time ago, quietly, before anyone was here to watch. The light of all those already lost galaxies is still arriving, like letters from friends who have long since moved beyond any address. And because the expansion is accelerating, that event horizon is, in a real sense, closing in. Not shrinking in the sky, exactly, but tightening its grip on which galaxies remain within reach. Right now, tonight, there are galaxies just inside the horizon whose light is still, barely, winning its race toward us. But as the expansion keeps speeding up, the space out there grows faster, and the horizon effectively draws in around us. One by one, those galaxies slip across it, from the side that can still reach us to the side that never will again. We are, quite literally, watching the doors of the sky begin to close. Slowly, so slowly, that across all of recorded human history, the change is far too small to notice. But steadily, and without pause, and without any force in the universe able to hold the doors open, the number of galaxies we will ever be able to see or signal or reach is not growing. It is falling. It has been falling for billions of years already, and it will go on falling until, in the deep future, almost nothing is left. Now I want to slow down and describe what that closing actually looks like, because the word closing makes it sound abrupt, like a door swinging shut, and it is nothing of the kind. When a galaxy drifts toward the cosmic event horizon, it does not simply wink out. It does not vanish in an instant. What happens is far stranger and much gentler, and if you could watch it over the eons, it would be one of the quietest sights in all of nature. The galaxy appears to slow down as it nears the horizon. Its light, already reddened by the expansion, reddens further, and further still, its colors sliding down out of the visible and into the deep infrared and beyond. And it dims, and it seems to freeze, hanging there at the edge, its final image growing ever fainter and ever redder, but never quite disappearing, an afterimage smeared across an infinity of time. If you have ever heard how things look as they fall toward a black hole, this will sound familiar, and the resemblance is not an accident. To a distant watcher, an object falling into a black hole appears to slow as it approaches the edge, to freeze at the horizon, to redden and fade and hang there forever, its last light stretched out across all the time there is. A galaxy crossing the cosmic event horizon does very nearly the same thing, for very nearly the same deep reason. It does not leave the sky with a flourish. It settles onto the horizon like a stone settling into still water, and reddens, and dims, and lingers, its last few photons trickling in over billions upon billions of years, each one longer and fainter than the last, until the light is stretched so far that no instrument could ever hope to catch it. And the galaxy has, for all purposes, quietly ceased to be part of our universe, present in principle, gone in every way that matters. A slow fade to black that takes longer than the age of everything. Now, before this starts to feel like a story with no shelter in it, let me give you the shelter. Because it is real and it is large. The expansion does not tear apart everything. It only tears apart what is not being held. And a great many things are being held, firmly, by gravity that is far too strong for the gentle push of dark energy to overcome. Down here, close to home, gravity is winning, and winning easily. And it will keep winning for as long as there is anything left to hold. Consider the scales. The push of dark energy is unimaginably feeble on any small scale. Across the width of a room, or a planet, or a solar system, or even a whole galaxy, its effect is so tiny as to be utterly negligible, drowned 1,000,000,000,000 times over by the ordinary gravity holding those things together. Dark energy only becomes the master out in the vast, nearly empty gulfs between the galaxies, where matter is so thinly spread that its gravity has almost nothing to grip. And the patient outward pressure of all that empty space can finally have its way. So the Earth is not expanding, the solar system is not expanding. The sun holds its planets exactly as it always has, and will go on holding them, untroubled, while the distant galaxies flee. Our own galaxy, the Milky Way, 100,000 light-years of stars wound into a slow, bright spiral, is bound tight by its own gravity and the great halo of dark matter around it, and it is going nowhere. It will not be stretched. It will not be pulled apart. The expansion happens between the galaxies, not within them, and it is not only our own galaxy that is safe. We belong to a small gravitational neighborhood, a loose gathering of galaxies bound together by their mutual pull, called the local group. There are a few dozen of them, most of them small, but 2 large ones, our Milky Way and the Great Spiral in Andromeda, along with a scatter of smaller companions. This whole little family is held together by gravity, and it too is immune to the expansion. The galaxies of the local group are not drifting apart from one another. If anything, they are drawing together. Andromeda, our nearest large neighbor, some 2.5 million light-years away, is not receding at all. It is falling toward us, slowly, on a long gravitational approach. And in a few billion years, something like 4 to 5 billion by most estimates, though the newest measurements have made even that a little less certain than it once seemed, the 2 great spirals will meet. But what actually happens when 2 galaxies meet? It will not be a collision in any violent, crashing sense. Galaxies are mostly empty space, and when they merge, almost no stars actually strike each other. Instead, the 2 spirals will slide through and around one another over hundreds of millions of years, pulled and stretched by each other's gravity, throwing out long streamers of stars, until eventually they settle down together into a single larger galaxy, most likely a great rounded elliptical blob of stars rather than a spiral. People have taken to calling this future merged galaxy Milkomeda, a soft blend of the 2 old names, which is either charming or a little silly, depending on your mood. The sun will very likely still be shining when it happens, out on its quiet arm, and the Earth may well still be here, its skies rearranged by the slow gathering of 2 galaxies into one. And after that, over further billions of years, the other members of the local group will fall in too, one by one, drawn together by gravity, until our whole little neighborhood has merged into a single island of stars. So that is the shelter, and it is worth holding on to as we go further out. Everything that is bound together stays bound together. The atoms in your body, the earth beneath the room, the sun, the galaxy, the whole local group, all of it held, all of it safe from the expansion, all of it drifting through the emptiness as a single gathered thing. The drifting apart is real, and it is relentless, but it happens between the islands, never within them. What is together stays together. It is only the distances between the islands that grow without end, but grow they do. And that brings us to the loneliest and most beautiful idea in this whole night. So let's approach it gently, because there is nothing frightening in it, only a kind of vast quiet. Beyond the local group, every other galaxy in the universe is receding from us, and the recession is accelerating. And one by one, over the ages, those galaxies are crossing the cosmic event horizon and fading from view. Not suddenly, in the slow reddening way we described, freezing and dimming at the edge of what can reach us, but steadily and permanently. And if you run the clock forward far enough, something happens to the night sky that is hard to feel the full weight of. Give it something like 100 billion years, perhaps 150 billion, a span many times longer than the present age of the universe. By then, the accelerating expansion will have carried every galaxy outside our own merged local group beyond the horizon. Their light will have stretched away into undetectable redness. They will be gone, all of them, the tens of billions of galaxies that fill our sky tonight. Every one of them slipped over the edge and out of reach, and an astronomer living in that far future, on some world orbiting some star in the great merged Milkomeda, looking out with the finest instruments they could ever build, would see beyond the stars of their own galaxy nothing at all, just their single island of light, and around it, in every direction, an infinite, empty, silent black. They would have no way to know the truth. And this is the part that stays with you. Everything we used to discover, that the universe is expanding, that it had a beginning, that it is vast and full of other galaxies, all of that evidence would be gone. There would be no other galaxies to see receding, so no way to notice any expansion at all. There would be no redshift to measure, because there would be nothing left out there to be redshifted. Even the faint afterglow of the Big Bang, that ancient light bathing all of space, would by then have been stretched so far by the expansion, its waves grown so enormous, that it would be smeared out below any possible detection, its wavelength longer than the horizon itself. Every clue would have been quietly erased by the very expansion the clues once revealed. This idea was worked through carefully by the physicists Lawrence Krauss and Robert Scherer in a paper they gave the quietly devastating title of The Return of a Static Universe and the End of Cosmology. And it has been explored by others too, including the astronomer Avi Loeb. And the conclusion they reached is one of the strangest in science. Those far future astronomers, looking out at their single lonely galaxy surrounded by an eternal empty dark, would do exactly what any good scientist does. They would observe carefully, reason honestly from what they could see, and build the best picture the evidence allowed. And that picture would be wrong. They would conclude, quite reasonably, that the universe consists of one island of stars, their own, sitting alone and unchanging in an infinite static void, with no beginning and no end. The very picture, in fact, that people on Earth believed for most of human history, before Hubble. They would have no expansion, no Big Bang, no other galaxies, no dark energy, none of it. And there would be no possible experiment, no instrument, however fine, that could ever reveal their error to them. The truth would be real and utterly unreachable. Sit with what that means for a moment, because it turns the whole story around and points it, gently, back at us. We are not living in an ordinary time. We are living in a rare and privileged window, a span of a few billion years, right near the beginning of the universe's long life, when the evidence of what actually happened is still visible in the sky. The galaxies have not yet fled beyond the horizon. The ancient light of the beginning has not yet been stretched into oblivion. The clues are still here, still arriving, still legible to anyone who looks. In the deep future, they will all be gone, and cosmology as we know it will become impossible, a science with nothing left to study. We happen to have arrived early enough to read the story before the pages blank themselves. That is not a tragedy. It is a strange kind of luck, and there is something almost tender in it that a young species on a small world got to look up during the one brief chapter when the universe still shows its workings. and understood, more or less, where it came from and where it is going, before the evidence drifts quietly out of reach forever. And it raises a soft, humbling question that is worth carrying, though not worrying over. If the far future hides its truths this completely, what truths might already be hidden from us? What did the universe erase in its first chapters before we arrived to look? Evidence that expanded away or faded out, or was swallowed before any eye could catch it. We may be reading a story with its opening pages already torn out, doing our honest best with what remains, exactly as those lonely future astronomers will do their honest best with far less. It is a reason for humility, not despair. Every generation of watchers gets the sky it is given and reads what it can and hands on what it learned. And ours, by luck of timing, was given a great deal. But let's follow the story further, past that lonely island galaxy. Because the emptying of the sky is only the beginning of the ending. It is the first and gentlest of the changes, the drifting apart of the galaxies. The universe does not stop there. Even that single surviving island of stars, alone in its dark, is not permanent. Because stars, however long they burn, do not burn forever. And so the next great chapter of the far future is not about distance at all. It is about the slow, quiet dying of the light itself. To think clearly about spans of time this enormous, it helps to have a map, and there is a good one. In the 1990s, around the same time the acceleration was being discovered, two physicists named Fred Adams and Gregory Laughlin worked out a careful timeline of the deep future of the universe, dividing its whole immense life into a handful of great eras, each one vastly longer than the last. It is a beautiful and sobering piece of work, a kind of calendar stretching so far ahead that the numbers lose all human meaning. And it gives us the stages of the long dying, one by one. We are, right now, near the end of only the first bright era, the age of stars. They called it the stelliferous era, the era of the making of light. And it is already, in cosmic terms, growing old. Here is how the age of stars ends, not with any drama, but simply by running out of what it is made of. Stars form from clouds of gas, mostly hydrogen, drawn together by gravity until they are dense and hot enough to ignite. But there is only so much gas in a galaxy. Every star that forms locks some of it away, and every star that dies returns only part of it, having burned the rest into heavier elements or trapped it forever in a dead remnant. So, with each passing generation of stars, there is a little less fresh gas to make the next. The galaxies are slowly using up their fuel. Star formation across the universe has, in fact, already peaked. It happened billions of years ago, and it has been declining ever since. We live just after the great age of star birth, in the long, slow afternoon of it. Fewer and fewer new stars are being lit, and one distant day, perhaps 100 trillion years from now, the last one will form from the last usable wisp of gas, and after that, no new star will ever be born again, anywhere, for the rest of time. And here is a gentle detail about which stars last the longest. Which ones would you guess? The answer is the opposite of what you might expect. The great brilliant stars, the blue and white giants, the ones that blaze across the sky and light up the beautiful pictures, are the ones that die youngest. They burn through their fuel in a furious hurry, in a few million years, and go out in the violence of a supernova. It is the small, dim, modest stars that endure. The most common stars in the universe are little red dwarfs, cool and faint, no more than a fraction of the sun's mass, glowing a dull red and sipping their fuel so slowly that they can keep burning for tens of trillions of years, some perhaps for 100 trillion or more. They are the tortoises of the cosmos, unremarkable and patient, and they will still be quietly shining long, long after the last of the bright, showy stars has died. If you want to know what the final embers of the age of light will look like, picture a sky with no brilliant stars left in it at all, only a scattering of dim red coals, burning lower and lower, the last fires in an enormous cold house, tended by nobody, going gently out one by one. And then, at last, they do go out. The final red dwarf fades, and the universe crosses into the next great era of its life, the one Adams and Laughlin called the degenerate era, which is a name drawn from the physics rather than any judgment, referring to the strange, dense states of matter that are left behind. It is the age after the stars. There is no new starlight being made anywhere, and the old starlight has faded. And what remains is a scattered collection of stellar corpses drifting through the growing dark. White dwarfs, the Earth-sized embers left when medium stars die, slowly cooling from white-hot to red to a dim, invisible cold, becoming what are sometimes called black dwarfs, though the universe is not yet old enough for a single one to have formed. Neutron stars, the impossibly dense cores left by the larger stars, spinning down and cooling in the black. Brown dwarfs, the failed stars that never quite lit, drifting on unchanged. And around and between them, planets gone dark and frozen. The cold, thin gas that could not be made into anything. And the vast, unseen dark matter, still there, still holding the dead galaxy loosely together, its gravity unbothered by any of this dying. It is a strange, still, patient age, the degenerate era, and it lasts a span that makes the whole history of the stars look like a single afternoon. Try to hold the proportions for a moment, though they resist being held. The bright age of stars, from the first stars to the last red dwarf, runs to something like 100 trillion years. That already dwarfs the present age of the universe, which is not yet 14 billion, by a factor of thousands. And yet the degenerate era that follows it goes on for vastly, vastly longer than that, so much longer that the whole age of stars becomes a rounding error, a bright flicker at the very beginning of a darkness that stretches almost beyond the reach of the numbers we have. During all of that immense time, the dead remnants simply drift and cool and occasionally, very occasionally, collide in the dark, and the accelerating expansion carries the whole thing further and further apart. Nothing much happens for eras upon eras upon eras, but even in that long stillness, matter is not quite as permanent as it looks, and this brings us to one of the deepest and least certain ideas in the whole far future. So let me flag the uncertainty clearly before I say the thing, because here we are truly at the edge of what anyone knows. The question is whether the ordinary building blocks of matter, the protons that sit at the heart of every atom, last forever. For a long time, it was simply assumed they did. The proton seemed utterly stable, eternal, the reliable bedrock of everything. But some of our deeper theories of physics, the ones that try to unify the forces of nature, quietly predict that even the proton might eventually decay, might fall apart, given enough time, into lighter particles and radiation. Not soon. The predicted lifetime is staggering, something like a number with 34 or more zeros after it in years, so long that in the entire age of the universe so far, essentially no protons should have decayed at all. We have looked for it. Deep underground, in enormous tanks of ultra-pure water watched by thousands of sensitive detectors, in experiments like the great Super Kamiokande detector in Japan, physicists have sat and waited, patiently, for even a single proton to fall apart, watching more protons than you could ever count, for years on end. And so far, they have never seen one do it, which does not mean protons are eternal. It only means that if they decay at all, they do so even more slowly than the simplest theories guessed, on timescales even longer than that already unimaginable number. So we genuinely do not know whether the proton is truly forever, or merely nearly so. It is one of the great open questions, and its answer decides the fate of matter itself. If protons do decay, even at that glacial, almost eternal rate, then the degenerate era carries within it its own slow ending. Over spans of time with those 34 or 40 zeros, every white dwarf, every neutron star, every cold dead remnant, every last atom of ordinary matter anywhere in the universe, will very gradually evaporate from the inside out, its protons quietly crumbling one by one into light and lighter particles, until the solid corpses of the stars have dissolved entirely into a thin drift of radiation and stray electrons and their opposites. The dead stars do not just cool. Given long enough, they cease to exist as matter at all, sublimed away into faint radiation by the slow failure of the proton. And when the last of the ordinary matter has crumbled, the universe enters its next and nearly final chapter, in which the only large things left standing are the darkest and most patient objects of all, the black holes. Black holes are the great survivors. They are what is left when gravity wins completely, when so much matter is packed so tightly that not even light can climb out, leaving a region of space sealed off behind a horizon of its own. They form when the largest stars die, and they sit at the centers of galaxies, some of them grown monstrous, millions or billions of times the mass of the sun, over the long ages of feeding. And when everything else has faded, when the stars have died, and the remnants have crumbled, and the ordinary matter has quietly evaporated away, the black holes remain, drifting through a vast and nearly empty dark, the last great structures in a universe that has forgotten how to make anything new. Adams and Laughlin called this the black hole era. It is an age of almost perfect stillness, ruled by objects that do nothing but sit and hold and wait, scattered further and further apart by the endless expansion. For a long time, it was thought that black holes were truly eternal, that once formed, they would simply persist forever, since nothing can escape them. But are they truly forever? In the 1970s, a young physicist named Stephen Hawking worked out something that surprised everyone, including himself. Black holes are not perfectly black after all. Down at the horizon, where the strange rules of the very small meet the crushing gravity of the very dense, a black hole very slowly leaks. It gives off a faint whisper of radiation, now called Hawking radiation, a thin trickle of particles and light seeping away from the edge of the dark. It is unimaginably feeble for any normal black hole, far too faint ever to detect from one, colder than the coldest thing you could name. But it is real, and it carries energy away, and energy is mass. And so, over time, a black hole that radiates is a black hole that is slowly shrinking. Given long enough, a black hole evaporates, and the times involved are where the numbers finally break free of anything the mind can hold. A black hole left over from a dying star, a few times the mass of the sun, would take something like a 1 followed by 67 zeros in years to evaporate away completely. The giant black holes at the hearts of galaxies, millions or billions of times heavier, take vastly longer still, up toward a 1 followed by 100 zeros in years, a span so far beyond the present age of the universe that there is simply no honest way to picture it. You cannot scale it down to a human comparison. There is no useful analogy. It is a length of time so great that every era we have talked about tonight, the whole age of stars, the entire immense degenerate era, all of it together, is less than the faintest flicker at the start of it. The black holes just sit there, in the growing dark, radiating their whisper of warmth into the cold, shrinking by an amount too small to measure across spans that make trillions of years look instantaneous. But shrink they do. And a black hole that has slowly bled away most of its mass grows hotter as it shrinks and radiates faster. And at the very end, after all those uncountable ages of patience, it finishes not with a whimper, but with a last bright flare, a final burst of radiation as the last of it evaporates and the black hole simply ceases to be. One by one, across the darkest and longest age of all, the black holes flare and vanish, the last of them, the greatest of them, going out in a final soft flash somewhere around that 1 followed by 100 zeros of years. And when the last black hole has evaporated, when even these great survivors have given themselves up to the slow leak of Hawking radiation, there is nothing structured left in the universe at all. No stars, no planets, no remnants, no black holes, nothing that could be called a thing, only the aftermath. And so we come, at the very end of the timeline, to the last and longest era of all, which is not really an era so much as a condition, a state the universe settles into and never leaves. Adams and Laughlin called it the Dark Era. It is what remains after everything else is gone. Picture it as gently as you can, because there is a strange peace in it once the fear wears off. The universe is unimaginably vast now, expanded beyond any describing. And still expanding, still accelerating, the last few particles it contains flung further and further apart with every passing age. And those particles are almost nothing. A thin, cold, ever-thinning drift of light, of the faint radiation left over from the evaporated black holes and the crumbled matter. A scatter of stray electrons and their opposites, so far apart that one might drift for an eternity without ever meeting another. And that is all. A dark, silent, nearly empty space, growing emptier forever, cooling toward a cold it approaches, but never quite reaches, the temperature sinking closer and closer to the absolute zero it can never fully touch. This is what the physicists mean by the heat death of the universe, though the name is a little misleading because it is not hot at all, but as cold as anything can be. The word heat here is really about a kind of evenness. In the beginning, and all through the ages of stars and structure, the universe was full of differences, of hot places and cold places, of dense clumps and empty gulfs. And it is differences like those that let things happen, that let energy flow, and stars burn, and life stir. The heat death is the state in which all those differences have finally been smoothed away. Everything is the same faint temperature, the same thin emptiness, everywhere. There are no more hot spots for energy to flow away from, no more fuel, no more structure, nothing left that can change into anything else. The universe has run all the way down, like a clock whose spring has fully unwound, and there is no winding it again. It does not end in fire, and it does not end in a crash. It ends in a stillness so complete that nothing can ever happen in it again, spread across a darkness so vast and so empty that the word empty hardly does it justice. Just the last cold light, drifting apart forever, in the dark, and never stopping. Now let me keep the promise I made earlier and tell you honestly where the doubt lives. Because a story like this should wear its uncertainty openly. There is something restful, not unsettling, in knowing the edges of what we know. Everything I have just walked you through, the endless acceleration, the emptying sky, the long dark, the heat death, all of it rests on a single assumption. That dark energy is a true constant, that the pushing energy of empty space has always been the same strength and always will be, exactly as Einstein's old term describes it. If that is right, then the future is more or less as we have told it, a runaway that never stops. And for years, that assumption has held up well against everything we could throw at it. But in the last couple of years, a crack of doubt has opened, and it is worth sitting with, gently, because it is the argument going on right now, tonight, among the people who study this for a living. There is an enormous new survey underway, using an instrument called the Dark Energy Spectroscopic Instrument, mounted on a telescope at Kitt Peak in Arizona, patiently mapping the positions of many millions of galaxies and quasars across billions of light years, building the largest three-dimensional map of the universe ever made. Its purpose is precisely to watch how dark energy has behaved across the history of the cosmos, to see whether it really has been constant or whether it has changed. And the early results, released across 2024 and 2025, have contained a genuine surprise. When the survey's data is combined with other measurements, it hints, softly, but persistently, that dark energy may not be perfectly constant after all, that it may, in fact, have been slightly weakening over the last several billion years. I want to be careful about how much weight to put on that, because the scientists themselves are being careful. The hint has not reached the level of certainty that physicists demand before they will call something a discovery. It might yet fade away as more data comes in, the way tantalizing hints sometimes do, dissolving back into the ordinary constant picture. But it might not. And if dark energy really is weakening rather than holding steady, then the ending of the story could be quite different from the runaway we described. A dark energy that fades might mean the acceleration does not go on forever. The expansion might, in the deep future, ease off or coast, or in some versions even eventually halt and turn around into a distant, slow collapse, bringing back one of those old endings that 1998 seemed to have crossed out for good. We simply do not yet know. The one thing the title of tonight's journey asserts so confidently, that it will never stop, turns out to carry a quiet asterisk, written in the newest data, still being argued over. There is a second argument running alongside that one, quieter, but just as unsettled, and it is worth a moment, because it shows how honestly unfinished all of this still is. It concerns something that sounds like it ought to be simple. How fast is the universe expanding right now? There are two good ways to measure that rate. One reads it off the ancient afterglow of the beginning, working out the expansion from the early universe and carefully carrying it forward to today. The other measures it directly, here and now, from nearby galaxies and their exploding stars. Both methods are careful. Both have been sharpened and rechecked for years by rival teams, and they do not agree. They hand back expansion rates that differ by a small but stubborn amount. The gap has not closed as the measurements have improved. If anything, it has hardened, grown too solid to wave away as anyone's mistake. Nobody knows why the two answers refuse to match. It is called the Hubble tension, and it is one of the liveliest open puzzles in cosmology tonight, a hint that there may be something about the universe, its expansion, or the things it is made of, that we still do not properly understand. It does not overturn the broad story of the drifting apart, but it is one more sign, if one were needed, that we are very early in this, and the sky still holds arguments we have not yet learned how to settle. But what if dark energy did the very opposite? There is doubt in that direction too, worth a moment for the shape of it. If dark energy instead grew stronger over time, rather than weaker, in the most extreme way some theories allow, then the future would be not gentler, but far more violent, and much shorter. This is an idea sometimes called the Big Rip. In it, the acceleration builds and builds until it becomes strong enough to overwhelm not just the gulfs between galaxies, but the gravity holding the galaxies themselves together, and then the gravity holding stars in their orbits, and then the forces holding planets whole, and finally, the very bonds holding atoms together, tearing everything apart from the largest scales down to the smallest, all in a rush at the end, in a finite time, rather than an endless one. The current evidence does not favor this at all. It is, if anything, the opposite of what the newest hints suggest, but it sits there on the menu of possible endings, a reminder that the fate of everything hangs on the nature of a thing we have only just begun to measure. And there is one more wild card, spoken of only quietly, the faint possibility that empty space itself is not in its truly lowest state, and could someday, somewhere, settle lower, sending out a change in the laws of physics that spreads at the speed of light. If that ever happened, it would arrive without any warning at all, which is exactly why it is nothing to lie awake over. You would never see it coming, and there is nothing anyone could ever do about it. So it asks nothing of you but a shrug. So the honest summary, the one to carry down into sleep, is this. The broad outline is clear and well supported. The universe is drifting apart, and the drifting is speeding up. Everything not bound tightly by gravity is slowly being carried beyond reach, and the sky will empty, and the stars will die. A great cold is coming, in the unimaginably distant future. That much the evidence tells us plainly. But the precise ending, whether the acceleration truly runs on forever, or eases, or reverses, or tears, depends on the deepest nature of dark energy. And that is a question we are only now, in these very years, beginning to be able to ask properly. We are living through the chapter where the answer is being worked out, and not knowing the last page of a story this large is not a failure. It is simply where a young species stands, early in its looking, doing its honest best with the sky it was given. But here is the thing that matters most, the thing that lets you set all of it down and rest. Every single event in this entire far future, even the very nearest of them, is so distant in time that it has nothing whatsoever to do with you, or with anyone, or with anything that any living thing has ever cared about or ever will. It cannot reach tonight. It cannot reach this year, or this century, or this age of the world. Let me give you the proportions, gently, so you can feel just how safe the present is. Our sun is not going anywhere for a very long time. It will keep shining, steady and warm, for something like another 5 billion years before it swells and dies, which is longer than the Earth has already existed. The emptying of the sky, the nearest of the great changes we have talked about, the drifting of the other galaxies beyond the horizon, does not really take hold for something like 100 billion years. That is more than 7 times the entire age of the universe so far. To get there, you would have to live the whole life of the cosmos, from the beginning until now, over and over, 7 times and more, before the sky even begins to empty in earnest. and the dying of the stars, the end of the bright age, lies 100 trillion years ahead, 1,000 times further still, and the crumbling of matter, and the evaporation of the black holes, and the final cold, lie so much further beyond even that the whole age of stars is a single bright morning at the start of an endless night. Now set your own life against those spans, not to feel small, but to feel safe. All of recorded human history, every empire and every song and every name anyone has ever known, fits inside a few thousand years. All of humanity, back to the first of us, a couple 100,000. All of life on Earth, back to the very first stirring in the ancient seas, not quite 4 billion years, which is less than a single day against the great calendar of the far future. We are not living near the end of anything. We are living at the very dawn. The universe is not old and winding down. By the measure of its whole immense life, it is a newborn, barely out of its first moments, and nearly the entire story still lies ahead, unwritten, in a future so long that the ending we have spent tonight walking toward is almost infinitely far off. The dark is real, but it is not close. It has never, for one instant, been close. So you can hold the whole thing lightly. The drifting apart, the runaway expansion, the emptying sky, the long cold, all of it is true. And all of it is happening. And none of it is a threat to anything you have ever loved or ever will. It is simply a fact about a future so distant that it belongs to no one. A beautiful and enormous fact about the shape of time, the kind of thing it is a quiet privilege to know, lying in a warm bed on a small world near the bright beginning of everything. You are allowed to find it lovely rather than frightening. Sit with it long enough, and it tends to become the first of those things rather than the second. And there is a deeper ease underneath even that, if you want it, for the nights when the far-off dark feels heavier than it should. The coming of that final cold does not reach back and undo the light that came before it. It does not erase the stars that burned, or the worlds that formed, or the living things that stirred and looked up and wondered. All of that happened. It is written into the history of the universe permanently. No amount of future darkness can reach back and unhappen it. That the brightness does not last forever is exactly what makes it worth anything at all. A sunrise matters because the day it opens will end. A life matters because it is finite. And the great bright chapter of the universe, this early age of stars and galaxies and warm worlds and curious minds, the one brief span in all of time when the cosmos is full of light and things are happening and someone is here to notice, matters all the more, not less, for being a small, bright morning at the beginning of a very long night. We happen to live in the morning. That is not a tragedy. That is the whole of the good fortune. So let all of it settle now, the whole vast story, and let it settle gently, because you have carried it far enough for one night. We have gone out to the very end of time, and it is time to come home. Let the numbers go first, the way you let go of a heavy bag at the end of a long walk. There will be no test in the morning. You do not have to remember what a Type 1a supernova is, or who Perlmutter and Schmidt and Rees were, or the difference between the observable universe and the event horizon, or how many zeros follow the one when a black hole finally evaporates. None of it was ever yours to hold. It was only ever something to listen to on the way down into sleep. A long, quiet story about a faraway thing, told softly in a dark room. The names can drift off now. The eras can drift off. Let the whole timeline, from the first star to the last cold light, slide gently out of your hands. It will carry on perfectly well without your attention, exactly as it always has. And as it drifts away, let's make the long journey back inward, all the way from the edge of time to the bed you are lying on, slowly, one scale at a time, the way you would descend a long staircase in the dark, feeling for each step. Come back from the far future first, from that final emptied dark, back across all those uncountable ages, back through the evaporating black holes and the crumbling remnants and the dying stars, back to now, to this early bright age, where the sky is still full of galaxies and the stars are still burning and the evidence of everything is still legible overhead. Come back to the universe as it actually is tonight, young and luminous and crowded with light, and begin, gently, to fall inward through it, toward home. Start at the largest scale there is, the one we can actually see. Picture the whole visible universe spread out below you, not as empty blackness scattered with stars, but as it truly is on the grandest scale, a vast and delicate web. The galaxies are not sprinkled evenly through space. They are strung together into long, glowing filaments, threads of thousands of galaxies stretched across hundreds of millions of light years. And those threads meet at great bright knots, where galaxies gather in their thousands. And between the threads lie enormous dark and nearly empty voids, hollow as bubbles, millions of light years across, with almost nothing in them at all. From far enough away, it looks like a cobweb hung with dew, or the branching of nerves, or the roots of some unimaginable tree, the largest pattern that exists, sketched faintly across the whole of creation. That is the cosmic web, the scaffolding of everything. And it is through this that the expansion works, slowly pulling the threads further apart, widening the dark voids, carrying the great knots of galaxies away from one another, across spans of time we have spent all night learning to hold. Let yourself hang there for a moment, above the whole lacy structure of the universe, and then begin to fall gently toward one particular thread of it, one glowing strand among countless others. Come down toward that thread, toward one modest knot within it, our own small gathering of galaxies, and find within it the little bound family we belong to, the local group. Remember what we said about it. This is the shelter. These few dozen galaxies are held together by their own gravity, immune to the drifting apart, bound to stay together while the rest of the universe recedes beyond the horizon. There is the great spiral of Andromeda, drifting slowly toward us across 2.5 million light years, in no hurry at all, on its long approach toward the merger that lies billions of years ahead. And there, beside it, one more spiral among the group, unremarkable from this distance, one bright wheel of stars among the others. That one is ours. Fall gently toward it now, toward the Milky Way, the galaxy that holds everything you have ever known. Come down into it, into the great, slow spiral, 100,000 light years of stars turning so grandly that a single turn takes longer than the time since the first fish crawled onto land. There are 200 or 300 billion stars here, wound into bright arms that sweep around a glowing center, drifting through the dark as one bound island that the expansion cannot touch. Fall inward, past the crowded core, out along one of the quiet spiral arms, past great clouds of gas where new stars are still being born, glowing pink and blue in the dark, past aging stars breathing their outer layers gently back into space, past the drifting remnants of stars that died long ago, out toward the calm middle reaches of one arm, far from the crowded center, in an unremarkable and peaceful neighborhood, until you reach one ordinary yellow star, one among the hundreds of billions, entirely unremarkable except for the small fact that it is ours, the sun, and gathered around it, held firmly in their steady orbits by its gravity, the small, familiar family of worlds, none of them drifting apart, none of them expanding, all of them circling just as they have for 4.5 billion years and will for billions more. Fall inward past the cold outer dark, past the great ringed giant, past the pale gas worlds, past the small red one, until you reach the third small world from the star, the pale blue one, the only one, as far as anyone yet knows, in all the vast web we just fell through, with anyone on it looking up and wondering about any of this. Come down toward it, toward the blue and white marble hanging in the black, the whole of every story ever told, wrapped in a thin, bright skin of air. Down through that thin shell of atmosphere now, the delicate band of air that holds all the weather and all the breathing that has ever happened, so thin that from space it is barely a line of blue at the edge of the world. Down through the high, cold clouds to the dark side of the earth, the half that is turned away from the sun right now, where it is night, where you are. Down through the dark to the land, to the wide, quiet region of it, to the town, to the street, to the roof over your head, and in through all of it, to this room, the room you are lying in right now, at the bottom of the whole long fall, at the still center of your own observable universe. Because everyone is at the center of theirs. The expansion made sure of that, long ago. Every raisin thinks it is the still one, and here, at the center of yours, is a bed, a body lying in it, breathing, in the dark. And here you are, at the bottom of the whole enormous fall, at the end of the long journey out to the edge of time and all the way back. A small, warm, gathered together thing, lying in a quiet room, on a small blue world, on one arm of one ordinary galaxy, in one bound little group, in one thread of the great cosmic web. Feel the weight of your body on the bed. Feel the places where you are held, where you are heavy, where you are still. The mattress beneath you, the covers over you, the quiet dark of the room around you. All of that unimaginable size and all of that unimaginable time. And here, at the center of it, is this, a body, breathing, in the dark. There is nowhere further in to go. You have arrived, and you are home, and you can rest now. And here is the gentlest truth of the whole night, the one to fall asleep holding. All of that drifting apart, the entire runaway expansion, the emptying of the sky, the great cold coming at the end of time. None of it can touch you here. The forces that hold you together, the ones that bind your atoms into molecules and your molecules into cells and your cells into the warm gathered body lying on this bed, are so overwhelmingly stronger than the faint push of dark energy that the whole expanding universe could not stretch you by the width of a single hair. The expansion works only out in the great empty gulfs between the galaxies, where there is nothing to hold. It has no power at all in a warm room, where everything is bound close and held tight. You are one of the small, gathered, held together places that the drifting apart can never reach. You always have been. You always will be, for as long as you last. And you are not separate from any of the story we told tonight. You are made of it, quite literally, woven out of the very history we followed all the way to the end. The hydrogen in the water of your body, in every cell of you, is very nearly as old as the universe itself, formed in the first few minutes after the beginning and drifting ever since, through space and clouds and stars, until some of it gathered into the world that became you. It is almost 14 billion years old, that hydrogen. And it was here long before the sun, and it will still be here, in some form, long after. And the heavier atoms, the ones that make you more than water, the carbon in every living cell, the oxygen you are breathing slowly in and out right now, the calcium in your bones, the iron in your blood, none of those existed at the beginning. Every one of them was forged in the hot heart of a star, cooked slowly under crushing pressure, and then scattered out into space when that star died, drifting for ages until it gathered into the cloud that became the sun, and the earth, and in time, you. You are made of the ash of dead stars. The bright early chapter of the universe, the age of light we are lucky enough to live in, is not just out there in the sky. It is lying in this bed, in the dark, listening to a voice describe where it came from. So let the whole vast thing carry on now, far away, in the deep, without you, because it does not need you, and it never has. There is a great relief in that if you let yourself feel it. The galaxies will keep drifting apart whether or not you are awake to picture them. The dark energy will go on doing its slow, patient, mysterious work in the great empty spaces, asking nothing, needing no witness, exactly as it did for billions of years before anyone was here to notice, and exactly as it will for billions more after we are all long gone. The far-off future will arrive on its own, in its own unimaginable time, with no help from you at all. Your only task tonight, the only thing being asked of you, is to lie here and be one of the small, warm, held-together places, and breathe, and let the rest of the universe take care of itself, the way it always has. You do not have to remember any of it. There is no test in the morning on the difference between the observable universe and the event horizon, or on why the expansion accelerates, or on what dark energy might turn out to be. Let the names go. Perlmutter, Schmidt, Reese, Einstein, Lemaitre, Hawking, Adams and Laughlin, Krauss and Scherer, all the careful people who worked this out. They did the work so that you would not have to, so that you could simply lie here and receive the story like weather. Let their names drift off gently. Let the numbers go, the billions and trillions, and the ones with 100 zeros. Let all of them slide out of your hands, because they were never yours to carry. They were only ever something to rest your mind on the way down into sleep, and let the day go too, whatever it was. It is behind you now, complete, in its place. You do not have to carry it forward or fix it or hold it up any longer. It is finished, and it is safe, and you can set it down. And let tomorrow go, for now as well. It is coming, on its own, gently, carried toward you on the same slow current that has brought you every day of your life. And you do not have to reach for it. It will arrive when it arrives. There is nothing to do tonight but be here in this one quiet moment, which is the only place you ever really have to be. Think, one last time, of everything we still do not know, and notice how little it disturbs the quiet of this room. We do not know what dark energy truly is. We do not know for certain whether the expansion will run on forever or someday ease or turn. We do not know whether the proton lasts for all time, or whether matter itself will one day quietly dissolve. We do not know the last page of the story. And none of that is a problem to be solved tonight. It is simply the honest edge of what a young species, near the bright dawn of everything, has managed to work out so far, lying under the same sky you are lying under now. The not knowing is not a weight. It is a gentle, open thing, and you can rest right in the middle of it and be perfectly safe. So let your breathing slow. Let the great web drift apart, far away in the deep, where it belongs, and let it be beautiful rather than heavy. Let the galaxies go on their long, slow journeys without you. Let the stars burn down in their own good time, 100 trillion years from now, with no help from you at all. Let the whole enormous future unfold on its own, in the dark, gently, endlessly, while you do the one thing it truly asks of you, which is nothing, which is only to lie here, held, warm, gathered, made of ancient light, and rest. The room is dark. The bed is holding you. The universe is drifting apart, far away, slowly, the way it always has, and it does not need you to watch, or to understand, or to stay awake for any of it. You only have to lie here and be one of the small held-together places, and breathe, and let go. Let the far end of time drift off to where it belongs, unimaginably distant. Let the names and the numbers fade. Let this one quiet moment be wide and warm and enough. There is nothing left to do but rest here and be held in a quiet, dark room near the bright beginning of everything. So just rest now. It will all still be here in the morning, exactly as it is, carrying on without the slightest need for your attention. And so will you. Good night.